Hi everyone, I hope you're all doing well. Today we're going to continue our discussion on buffers, and we were calculating the pH of a buffer system previously, but what if we add an acid or a base to a buffer? We would hope that the pH would stay relatively the same because that's the purpose of a buffer, but it is going to change slightly. So how do we calculate that change in the pH? So we're going to break up the problem into two parts. First, we're going to perform a stoichiometry calculation. So what we're going to do is we're going to calculate the new concentrations of acid or base depending on what we're adding. So for instance, if we add acid to a buffer, we know that it reacts with the base in the buffer, and that's going to create more of the initial acid. But if we add a base to the buffer, that's going to react with the acid to make more of the initial base. So we need to determine how the concentrations of the original acid and the original base are changing after the addition of outside acid or outside base. Then, once we know the new concentrations, then we can perform an equilibrium calculation of the concentration of hydronium ions using the new initial values of the acid and the base. So that's a lot of words. Let's actually do a practice problem. But actually first, I want to show you a visual of what's going on here. So in this figure, we have our buffer in the middle. And initially we have equal concentrations of weak acid and its conjugate base. But then if we add base to this buffer, that's going to react with the acid. So we're going to see a decrease in the amount of acid after it reacts, and we'll see an increase in the conjugate base. So up above, or actually down below, I'll write out the reaction that's occurring here. So the acid is reacting with base, and remember that bases are going to accept hydrogen ions, and acids are going to donate hydrogen ions. So we would end up with H2O and the conjugate base of the acid. So we're going to see an increase in concentration of that conjugate base. Now, on the other side, what if we add an acid? The acid is going to react with the base in solution, so the concentration of that base is going to decrease, and we're going to end up with more of the original acid. So let's show that reaction. So again, that conjugate base is going to react with acid to produce more of our original acid that was in the buffer. So we need to figure out what are these new concentrations of acid and conjugate base after we add an acid or after we add a base. And then once we know those concentrations, we could use, for instance, the Henderson-Hasselbalch equation and determine the pH of solution. So let's go over an example problem, and this problem is in your textbook. And in your textbook, they solve this problem using two different methods. So they use both the original method that we were using to calculate pH, and then they also show the Henderson-Hasselbalch equation. Now I'm going to use the Henderson-Hasselbalch equation because it is super useful and it's a lot easier than our original method. But in this example, we have a 1 liter buffer solution that contains zero point 0.1 moles of acetic acid and zero point 0.1 moles of sodium acetate. So this is our buffer that we had previously talked about, and we also calculated the pKa for this acid before. Now the value of Ka for acetic acid is 1.8 times 10 to the negative fifth. And because the initial amounts of acid and conjugate base are equal, the pH of the buffer is equal to the pKa. So remember from the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the base concentration over the acid concentration. But if the concentrations of the acid and the base are the same, then the log value is going to cancel, and we just end up with pH equal to pKa. And the pKa for acetic acid is 4.74. So now we're going to calculate the new pH after adding 0.01 moles of solid NaOH to the buffer. For comparison, let's calculate the pH after adding 0.01 moles of solid sodium hydroxide to 1 liter of pure water. So there are a couple of different things here. We're going to calculate the pH after we add some sodium hydroxide to the buffer. And then we're going to compare that to the pH of sodium hydroxide in pure water. So this will demonstrate how a buffer can maintain a particular pH value or an approximate pH value. Okay, so I minimized the text here and bolded the part that we're going to work on. So first we're going to calculate the new pH after adding 0.01 moles of solid sodium hydroxide to the buffer. Now, the key point here too is that we're adding solid sodium hydroxide, so we're not changing the volume of the solution. So let's start by writing out the reaction between the buffer and sodium hydroxide. So remember that sodium hydroxide dissociates in solution to produce sodium ions and hydroxide ions. So this dissociation occurs about 100%. So there's 100% ionization here, or we can assume that, especially because sodium hydroxide is a strong base. So if we have 0.01 moles of sodium hydroxide, that means we have 0.01 moles of hydroxide ions in solution. Now, when we add hydroxide ions to solution or to our buffer, remember that it's going to react with the acid in the buffer. Okay, so we can show that this reaction will produce water because the base is going to grab onto that hydrogen from the acid. And then what's left over is the conjugate base. All right, so instead of an ice table here, we're actually going to write out a slightly different table. So before the addition of hydroxide, we had, let's see, 0.1 moles of acetic acid. We didn't have any hydroxide because this is before the addition of hydroxide. And the amount of base was 0.1 moles, or the conjugate base. Now the addition step involves adding 0.01 moles of hydroxide. So after the addition of hydroxide, we're going to see that some of the acid reacts with that amount of base. So the amount of acid will be 0.1 minus 0.01. So we would end up with 0.090 moles of our acid after the reaction occurs. And then the base should all get used up. So we'll have 0 moles of our base after the reaction. And then in terms of the conjugate base, we're going to see an increase in the amount of conjugate base. So we're going to actually see an additional 0.01 moles of conjugate base. So that equals 0.110 moles of the conjugate base. All right, so you'll notice that we just stuck with moles here. We didn't calculate concentrations, and that's totally fine. You can use moles in these tables. You don't always have to use concentrations. And sometimes dealing in moles is a little bit easier because you can ignore any possible changes in volume. And then later you can calculate the concentrations. Okay, so remember, we're going to use the Henderson-Hasselbalch equation for this problem. So we're not going to do this the previous way that we were solving these problems, but your textbook does show how to do it the original way, which if you prefer that way, you can step through that. Okay, so let's write out the Henderson-Hasselbalch equation. Okay. Now, we do need the concentrations of the acid and the base for this problem, but remember that the volume for both of our acid and base is 1 liter. So if we take the amount of moles of acid and divide it by 1, we get the same value back that we had before. Same for the other component. So we can just plug in the amount of moles for both. All right, so up above in our problem here, we were told that the pKa of this buffer is 4.74. So we're going to plug that in. And then we're just going to plug in those mole amounts that we calculated, because again, the volume is the same for both the base and the acid, so they essentially cancel out. But we said that there were 0.110 moles of base and 0.090 moles of acid. So if we plug that into our calculator, we should find that the final pH is 4.83. So remember that the original pH was 4.74. So by adding 0.01 moles of base, we did increase the pH a little bit, but we're also going to compare this to the pH of sodium hydroxide in pure water, and we'll see that the buffer did a pretty good job of maintaining this pH. Now, first, we should check that the Henderson-Hasselbalch equation works in this instance because remember, we want the percent ionization to be less than 5%. So let's just do a quick check, make sure our calculation makes sense. So remember, when we're checking the Henderson-Hasselbalch equation, we want to first find the concentration of hydronium ions and then compare that to the initial concentration of acid. So the concentration of hydronium ions will equal 10 to the negative pH. And we said that the new pH is 4.83. So if we plug that into our calculators, we should get 1.47 times 10 to the negative fifth moles per liter for our concentration of hydronium ions. So now let's compare that to the original concentration of acid, which we said was 0.09 after the addition of base. Okay, now when we calculate this, we should get 0.016%. So that is much less than 5%. So this is a valid use of the Henderson-Hasselbalch equation. All right, so now let's perform that second calculation. Let's determine the pH of NaOH in pure water. So remember from earlier that when NaOH is added to water, it completely dissociates into sodium ions and hydroxide ions. So if we have 0.01 moles of sodium hydroxide, that means we also have 0.01 moles of hydroxide in water. Now, in order to calculate the pH, we need the concentration of hydronium ions. So there's a few different ways to do this. You could use the fact that pH plus pOH is equal to 14, or you could use the fact that the concentration of hydronium ions times the concentration of hydroxide ions is equal to the ion product constant. So let me write those out. So for instance, in the first option, you could calculate the pOH using the concentration of hydroxide ions, and then plug that into this equation and solve for pH. Or in the second option, you could calculate the concentration of hydronium ions using that equation and then calculate the pH using the concentration of hydronium ions. Both methods will give you the same answer. It's just what you prefer to use. I'm actually going to use option 1. So let me just erase these here. But you can use option 2 as well. So if we're going to calculate the pOH, we need the concentration of the hydroxide ions. So we have 0.01 moles of hydroxide, and we're dividing that by 1 liter of water. So our concentration is 0.01 moles per liter. Easy enough. So now, to calculate the pOH, we're going to plug in the concentration of hydroxide ions. So we're going to take the negative log of 0.01, and that should give us a value of 2. Now remember, on the pOH scale, the smaller the pOH, the stronger the base. So this makes sense. Now to calculate the pH, we're going to subtract the pOH from 14. And that should give us a value of 12. And remember, the pH scale is opposite from pOH, so the higher the pH, the stronger the base. Now remember, we're comparing this to our buffer solution. When we added base to our buffer solution, the pH was 4.83. So the buffer does a really good job of maintaining a specific pH value or range, whereas water, which is not a buffer, cannot control the pH. So buffers are super useful if you do need to maintain a particular pH. Now let's work on worksheet problem 3. And in this problem, for each of the following solutions, we're going to calculate the initial and final pH value after adding 0.1 moles of sodium hydroxide. So in A, we're going to determine the pH of pure water. So initially, pure water should have a pH of 7. And then we're going to determine the pH after adding 0.01 moles of sodium hydroxide. And then in B, we're going to add sodium hydroxide to a buffer solution. And then in C, we're going to add sodium hydroxide to a different buffer solution. So again, we want to determine the pH before addition of sodium hydroxide and after addition of sodium hydroxide. Okay, so let's determine the pH of sodium hydroxide in water. So again, we have sodium hydroxide, which completely dissociates into sodium ions and hydroxide ions. So if we're starting with 0.01 moles of sodium hydroxide, we'll end up with 0.01 moles of hydroxide ions in solution. Now, for this problem, we don't have an easy 1 liter volume of water. It's different this time, so we're going to have to calculate the concentration of OH. It's going to take a little bit longer. Let's see, so we have 0.01 moles of hydroxide in 250 milliliters of water. So what would 250 milliliters be in liters? So you should have said 0.25. And you can also plug that into your calculator, that's fine. Okay, so now what is 0.01 divided by 0.25? You should get a concentration of 0.04 moles per liter. And I'll add another 0 on there for sig figs. Okay, so now we have what we need to calculate the pOH. And this should give us a pOH of 1.40. So then to determine the pH, we're going to subtract the pOH from 14. and we get a pH value of 12.6. So remember, our initial pH of water should be 7, and now our final pH after adding sodium hydroxide is 12.6. So sodium hydroxide in pure water significantly increases the pH value. But let's see what happens when we add this sodium hydroxide to a buffer. All right. So in this solution, we need to determine the initial pH. So we have our acid, HCHO2, and our base. So this is potassium bonded to CHO2 minus. All right. So to calculate the initial pH, what we can do is use the Henderson-Hasselbalch equation and then just plug in the Ka value for the acid, and then we'll plug in the concentrations that we were given. Okay, so let's determine the Ka value for our acid, and you can look this up in your textbook, but I'll just give it to you here. It is 1.8 times 10 to the negative fourth. So now we can determine that pKa value. And we can plug in the concentrations of the base, which was 0.275, and the acid, which is 0.195. So once we plug in those values into our calculator, we should get a pH value of 3.89. So that is our initial pH of the buffer. So now let's see what the pH is after we add sodium hydroxide. Now, in order to solve this problem, we might want to just convert everything to moles, because we can then directly compare the amount of sodium hydroxide that's added to solution to the amount of weak acid and conjugate base. So I'm going to calculate the number of moles of acid and the moles of base. So starting with acid, we have 250 milliliters, so I'll convert that to liters, and then use the concentration of acid to get to moles. So this should give us 0.0488 moles of our acid. And then we can do the same thing for the base. We have 250 milliliters of our solution, and then the concentration of the base is 0.275. So we should end up with 0.0688 moles of the base. All right, so now what we can do is make a table similar to the one we made in our example problem. So we'll determine how the amount of acid and base changes after we add sodium hydroxide. So let's write out the equation for the reaction between the weak acid and sodium hydroxide. And I'm drawing a single arrow here because we are adding strong base. So this reaction will occur, and we shouldn't really see a reverse reaction. So our products here would be water and the conjugate base. So now, before addition of the sodium hydroxide, we said that we had 0.0488 moles of the weak acid. And then we won't have any of our hydroxide initially. And then we had 0.0688 moles of the conjugate base. So now we're going to add 0.01 moles of hydroxide. And then after everything reacts, we'll see that some of the acid is used up to react with the base. So we're going to lose 0.01 moles of acid. And everything here is reacting in a 1-to-1 ratio, similar to our example problem. So we don't have to take stoichiometry into account, really. So after everything reacts, we'll have 0.0388 moles of weak acid. We're going to have 0 hydroxide ions left. And then for the base, or the conjugate base, we're going to see an additional 0.01 moles of conjugate base. So that will give us a total of 0.0788 moles of the conjugate base. So these are our new amounts of the weak acid and the conjugate base. And now we can calculate their new concentrations and plug them into the Henderson-Hasselbalch equation. So let's, oh, whoops. Oh, I didn't give myself enough room here. So let me actually exit out. And I'm going to duplicate this slide. And then I'm going to erase. Clear pen markings. Oh no, it's not going to let me erase. Oh, okay. Let's see if I can just put in a blank slide. There we go. All right, so let's finish solving this problem. I'm going to delete this duplicate I made. Isn't technology great? Okay, so for the last part of part B, we're going to calculate the new concentrations of our acid and our conjugate base. So we said that our new amount of acid is 0.0388 moles. And then the volume of solution has not changed because remember we were adding solid sodium hydroxide. So the solid is not going to have an effect on the volume. All right, so we'll divide this by 0.25, which was our volume. And this should give us 0.155 moles per liter for our new concentration of acid. And now we can do the same thing with the conjugate base. So we found that the new amount of conjugate base is 0.0788 moles. So we'll divide that by the same volume to get the new concentration. And once you plug that into your calculators, you should find that the new concentration of conjugate base is 0.315 moles per liter. So now we should have everything we need to calculate the pH after the addition of sodium hydroxide. So to find the pKa, we're just going to take the negative log of the Ka value that we used before. So the Ka value of our acid was 1.8 times 10 to the negative fourth. And then the concentration of base we just found out was 0.315. And then we can divide that by the concentration of acid. And this should give us a pH of 4.05. So remember that our initial pH before the addition of sodium hydroxide was equal to 3.89. So the pH didn't change by very much after the addition of hydroxide. And this is compared to our first problem with water, part A, where we saw that the addition of sodium hydroxide drastically changed the pH value of water. So again, buffers do a really good job of maintaining pH. Okay, so for part C, I would like you to try this. Oops, there we go. So for part C, I would like you to try this on your own. And I will post the key to worksheet for chapter 17, and then you can compare your answer. Now, we did work with this buffer previously, and remember that this is our acid, or sorry, our base. Getting things mixed up as usual. And then this is our acid. So we have ethylamine and its conjugate acid. So there should be a positive sign and a negative sign here. And the chloride ion is just balancing out the charge on the conjugate acid. All right, so good luck. And if you have any questions, please feel free to email me or set up an office hour through Calendly. And remember, the link to Calendly is on the homepage of the Canvas website. All right, so I will see you all in the next video.